Well, greetings, mathletes, and welcome back. This is part 2 of our function transformations lecture. And we have 4 specific functions to look at today. And these are functions that you should have at least some familiarity with. One is the squared function, x squared. The other is x cubed, which is the cubic function. And then we also have the absolute value function and the square root function. And so we're going to be transforming all of those. And these functions have some similarities which do actually make things quite nice. And so I'm going to start out by not showing you, but reminding you what they look like, and then going through some guidelines that will help us graph these a little bit easier. We've already seen what all the transformations do in the last lecture. Now we need to see how that works out in practicality when we're actually doing the algebra. So let's go ahead and get started. Now you'll also be able to find these functions in the reference sheet that I posted in the module as well. But the functions we are going to look at are f of x is equal to x squared, right? And that, I'm just going to do a quick sketch of each one so we know the basic shape. It goes through the origin and has this U shape. Then we have f of x is equal to x cubed, and that has a basic shape. Well, that's not real good. Let's try that again. Of something like this. Well, that wasn't as smooth, but it probably hugs the curve a little better. It looks something like this. Then we have f of x is equal to the square root of x. And this one actually only has positive values, right? Square roots only spit out positive values, but you're actually only allowed to put in positive values. And it ends up being a half of a parabola like this. And in fact, it's actually the inverse function for the right half of a parabola is what it is. And then the last one is the absolute value function, the absolute value of x, which has a V shape, right? And we know absolute values only let positive things out of the function, and so they have to all be positive values. And so we end up with two lines. That didn't work out right. Seems like when we get a little lower in the board here, the accuracy of where my pen is gets worse. Okay, but it has a V shape. And the right-hand side has a slope of 1, and the left-hand side has a slope of -1, right? They're two lines that meet up at the origin. Now, one of the similarities between all of these functions is that they all go through the origin, right? Every one of them goes through the origin. And then on top of that, there's even more. All of them go through the point 1, 1. Right? The point 1, 1 is part of each and every one of these graphs. Right? So those are two really good anchor points, because if you can figure out where the origin moves to, you can move the whole function over there. And then if you can figure out what happens to the 1, 1, that tells you how much things have stretched or churned. And so those are the things that we're going to be looking at. So here are the guidelines that we can follow as we go through this. So 1, if I multiply a function by a, what that does is that takes the point 1, 1 and it turns it into the point 1a. Now, here's why, is because by multiplying a by f of x, what you're doing is you're multiplying all of the y values by a. That includes this y value, this 1 here. So that's also going to be multiplied by a. So that's a good guidepost. 2, look for reflections. Ooh, not loof for reflections. Let's try that again. Look for reflections. Right? So that's negative f of x or f of negative x, right? And you just know which way that's going to reflect them. 3, and this is the one that probably is carrying over from an algebra class or something like that, is that if I have f of x minus h plus k, right? So if the function's been transformed in this way, what that does is it takes the point 0, 0, and it maps it to the point hk, right? So that means that these anchor points here would move to wherever hk is. Okay, so those are some of those are basically the guidelines that I like to follow when I'm graphing these things. I figure out how the actual shape has changed, and then lastly, I figure out where it went to, and then I draw the same shape. Oh, so that's how we're going to be going through this. Okay, so let's go ahead and clear this off. And yeah, there we go. Okay, so let's go ahead and look at our first example here. So we have h of x is equal to 2 times x minus 2 squared plus 1. Okay, so first we have to figure out which function we're starting with here. And since we see that the term that has x in it is being squared, this term right here, that means that it's some form of a parabola, right? It's some form of the x squared function. Okay, now we know, and let's see, what color should I do it in? I'm going to go ahead and start the original function in black. So we know originally we have 0, 0, 1, 1. This is just x squared, by the way. I'm going to graph this one first. Once you get good at this, you don't have to graph the original function first. Once you're familiar enough with it, you can picture it in your head and do all this stuff. The goal here is so that you can actually just look at something like this and know what it looks like. So in any case, with x squared, if I put in 2, that means I'm up to 4. So I can already see I have some kind of shape like this. And then I can map the same points on the opposite side here. Ooh, I thought I could. Well, we get the idea. Okay, so it's something like this, right? Particularly, we're paying attention to 0, 0, and 1, 1. So first thing to note, there's a 2 here. That's our A, right? So that means that the point 1, 1 now maps to the point 1, 2, right? Because it's A times 1. So it's 1A, A is 2. So that means the new shape of the graph, and since it's symmetric, these things, they map on both sides, you can draw the other one here, and we can see that multiplying it by 2 has basically doubled. What it's doing is doubling the distance between this y value and the x-axis, right? So we're getting this shape now. Okay, so it's narrower. And we know that wherever the origin goes, if I go up 2 and over 1, there's another point. And that's going to be true even when we shift it. So now we know the shape we're looking for. Are there any reflections? Well, the 2's not negative, and there's no negative in front of the x. So we're good as far as reflections go. Now what we need to do is figure out what h and k are, right? Because 0, 0 is going to map to hk. Now, one of the things I want that I may not have pointed out directly, hopefully you remember it. If I have f of x minus h plus k, 0, 0 maps to hk. You notice this h doesn't have a negative. This h does. Okay, so if this one doesn't have a negative and this one does, what that means is those are opposite signs. So here, this is x minus 2, which means h is positive 2. So now we're at positive 2. And the y-coordinate stays the same, right? It's plus k, and this is a positive k also. So those are the same sign. So the x values are the opposite sign, and the y values are the same sign. right? So that means, and I'm just making sure I have the right color because I'm going to match it to our original function. We're switching to the point 2, 1, which means this 0, 0 moves over to here, right? If I want that second point, this guy, I know I go up 1 and over 1 to get that. I can do the same thing with the point on the other side, up 1 and to the left. And now I can draw in the actual graph of this function. And that's going to be the graph in purple. So you notice how I kind of, I'm trying to make it bold here. But you notice how I did it a step at a time. I decided what the shape was going to be, and then I figured out where it goes to. Now, there's no law that says you have to do it in this order. It's just the order that makes sense to me. But you're absolutely welcome. If you can get the correct answer doing these steps in another order, there's no law that says they have to be in the order I'm advising. So if you can figure it out another way, I'm okay with that. One of the other things that people do when they're graphing something like this, if they can figure out where the HK is, right, this point, what they'll do is just plug in X values into the original function on either side and see what their Y values have to be to generate more points. So once you figure out where 0, 0 went, you could just plug in points on either side of that value as far as the X's go, and you can figure out what the rest of the shape is. So there is a direct way to compute it. As a matter of fact, when people were trying to figure out what these shapes looked like, that's how it was done. In fact, that's how your computer does it, or your graphing calculator. It generates the graph 1 point at a time. Human brains are nice because we can manipulate things abstractly, so we don't have to do it 1 point at a time. Okay, so just to quickly review what we did, right? We were given our function. The first thing we looked at was this 2, and we said, oh, that 2 is going to change things. Let's see how it stretches. And so we did this. 1, 1 went to 1, 2. So that point got moved up. And then once there were no reflections, so we moved on to the next point, which was what happens with 0, 0. And 0, 0, we see from here and here, moves to the point 2, 1. And so that's where the function rigidly moves. It's a rigid motion. It doesn't change shape. It just moves over when you're only looking at H and K. We've already figured out how the shape changed. Okay, so that's the basics, and that's what we're going to be doing with each and every one of these. We're going to walk through it, figure out how the shape changed, and then figure out where it moves to, right? Of course, accounting for reflections. We didn't have any in this one. So, all right, let's look at the next example. Okay, and then see if I can. Oh, it's not working quite how I wanted, but okay. There we go. All right. Oh, accidentally grabbed that. Get that off of there. All right. So the next equation. Let's look at g of x is equal to 1/2 times x minus 3 cubed minus 2. Okay, so again, remember the cubic function, just real quickly, has this kind of a shape, right? So that's just to remind you. Again, it goes through 0, 0, and 1, 1. But just knowing that, let's see what you can do with this, right? So go ahead and pause it here, see what you can get, and then we'll walk through it together. Okay, so pause. Okay, so let's go ahead and take a look. Let me go ahead and get this off here so we can write. Okay, so again, in your head, you want to be thinking about what the cubic function looks like. You know it goes through oh, that's eraser still. Let's try this one more time. It goes through 0, 0, and it goes through 1, 1, right? And it does one of these deals where it goes up real fast And it does, because by the time you get to 2, the cubic function's at 8. And the same thing here, it goes through the -1 and it goes down this way, right? So it looks something like that to start with. Let's see here. So let's start by seeing how this thing is either stretched or compressed. We have a 1/2, so that means that the point 1, 1 maps to the point 1, 1/2, right? Because A is 1/2 this time. So that means we're compressing it in this direction, because 1, 1 moved down to 1/2. So that means all the distances from the x-axis are now cut in half. And we can draw this in. Right? And it should do the same thing here. It should go through there. So it's widening it is what it's doing. Right? It's smashing it down this way. But it does make it look like it's wider. Okay, so we have the little bit wider shape. So let's see here. I don't have any reflections. X isn't negative and the 1/2 isn't negative, so I don't have to worry about that. Now all I have to figure out is where 0, 0 went. Right? So this will be our 0, 0 goes to, let's see here, that's -3, so that means it's a +3. -2, we're going to keep the minus on that, right? The y-coordinate keeps the sign, the x-coordinate switches the sign. So that means this 0, 0 is at the point 3, -2. So it's moved all the way down here, right? But everything else is still true. I know if I notice here, I move to the right 1 and up 1/2. So that means I have a point there. And the same thing is true over here. And that means that my new shape does one of these deals. Right? So the new shape should be something along those lines. And it should specifically go through these points here. Right? Okay. So that's our second example. So let's go ahead and take a look at our third example. Let me go ahead and get rid of that, delete. Okay, so the next function we're going to look at, let's do, get the pens on. G of x is equal to -3 times the absolute value of x plus 2, right? Now this one, I don't even want to give you any prompting. I just want to see if you can do this. And actually, I won't be able to see it all, but you'll be able to see if you can do this. And this will let you know if you're understanding this so far. So see what you can do with this one, and then we'll walk through it together. So go ahead and pause it here, and then we'll work on, when you're ready, push play again, and we'll work on it together. Okay, so we know that the absolute value, if it has been unaltered in any way, basically gives you two lines that meet up at the origin, and they make this V shape, right? So you get something like this. And so we need to figure out what happens here. So again, we're going to see what happens to this point 1, 1 to start with. So first of all, 1, 1 is going to, again, map to 1a. And in this case, a is -3. Oops, why did I don't need the absolute value on that. There we go. But this case, a is -3, right? So that means from here, it's now here. That's kind of interesting. Yeah, and what that means is that negative, by doing it this way, we just accounted for the reflection as well. Right? So if you recognize that a is negative and you just use it this way, it gives you the reflection. You don't have to even look at it as a separate thing. And that means that I'm going to be down here also. So that means that my absolute value has been narrowed and flipped at the same time by that -3. I feel like I should put a little head on this. It looks like the Pearl Jam cover of 10 or something. Anyways, or is that alive? I don't remember. It's been a while. Nonetheless, so we have the shape of this thing. Now all we have to do is see where it moves to. right? So let's see what happens to 0, 0. So 0, 0, let's see what happened. The x value should be at -2, and there's no y value hanging out back there. One of the things that you want to remember is if it's not written, it's a 0, right? It's a +0. So that means that let's try that again. The point where the origin moves to is -2, 0, which is over here, right? And we already know the shape. I go down 3 and over 1 from there to get this. Oh, I didn't mean that to be red. I meant it to be purple. So it matches the original function. And then let's see, down 1 over 3. So that's that one. And now we just need to draw it in. Right? So what's in purple here is our actual function. It's this guy. I'm trying to draw it bold, but it's not. I should probably just make the line thicker. It'd be easier. But you get the idea. Okay. So there's that one. And we also got to see what happens when we just don't see something there. It's a 0. Incidentally, if this had been something like, the absolute value of x plus 5, you want to think of that as the absolute value of x minus 0 plus 5, right? It's in there. Or you can make it plus 0. It actually doesn't matter with 0. I put the minus, so it's in the x minus h form. So keep that in mind. You can always plug it. You can always put zeros in places where there's nothing written. Okay, so we have one more example to do after this, and then I want to talk about a couple of other things to look out for. But here's our next example. Let's go ahead and clear this off again. Let's see here. I'll go ahead and do that. There we go. And all right, so let's look at our last example here. So let's make our function, let's make it f of x is equal to, what do I got? The square root of -x plus 2 plus 1. Okay, so first things first, you note that a is 1 in this case because there's nothing written out here in front of the absolute value in front of the square root. So there's a 1 there, right? It's being multiplied by 1, which means there's no vertical stretch or compression, right? It's just it's the size it's supposed to be. But it is a square root function, so we need to look at what the square root function looks like. If you have trouble making it, just think in terms of square roots. The square root of 0 is 0. The square root of 1 is 1. 2 is not a perfect square. Just jump up to the next perfect square. The square root of 4 is 2, right? The square root of 9 is 3. So you can actually map this whole thing out. Right? So it looks something like that. That's what we're going to be manipulating. So we did that. Now we need to look for reflections. Now, there's no negative out in front of the square root, but there is a negative on the x. And these are tricky. The ones that are inside the function actually they'll cause you fits if you forget to do this because you'll keep getting the wrong answer. If you're going to accommodate a negative here, because it is going to be flipped, that negative is going to flip it across the y-axis. So it's going to be pointing to the other side. It's going to be pointing this way instead of the direction it's pointed right now. So what you have to do is you have to factor the negative out of this whole term before you really start thinking about it. So this is actually the same thing as the square root of -x minus 2 plus 1. Okay, so let's see what actually happens with this flip. Now, we just said it's gonna change the direction. So it was pointed this way. Now it's going to be pointed this way. So this is, oh, that's an eraser. This isn't going to change, but all these points become the negatives over here. So this thing is now going to go, but this is hard to draw. There we go. It's going to come in from this side. So we've reflected it across the y-axis. Now we have to move it to the appropriate point. So 0, 0 goes to the point 2, 1, right? 2, 1 is right here. So what that means is now our function looks like this. We need it to go to the left like this one in blue here. And we'll go, it's going to go off this way, right? We're going to have to forgive the poor drawing, but you get the idea, right? You figure out how the shape, the orientation changes, if it's stretched or skewed, or stretched or compressed, and then you want to see if it's been translated. So you're actually looking for all of these separate things separately. Okay, now the thing I wanted to point out to you is that anytime you have a function like this, whenever you have f of negative x plus h, right? If you minus h, well, it is plus h. Anyways, whatever's in here, whatever's inside of that function, whether it be a cubed function, a squared function, an absolute value function, no matter what it is, you can't actually find the value of h until you pull the negative out of that whole term. So you have to change it to x minus h, right? Just to be able to read it consistently. You really need to think about it this way. It's the same thing with trig functions. Whenever you have that negative on theta, you have to factor it out of that whole term if you actually want to understand what's happened to the sine or the cosine function. So it's the same kind of thing, but this is a place where lots and lots of people just go nuts because it's such a simple thing to forget. I want to point out too that often instead of negative x plus h, it's written this way, h minus x, right? And you have to be able to switch it to this. Those are the same things because h minus x is the same as negative x plus h, and you need to move it into this form, right? So those are some things I just wanted to warn you about, just in case you run into trouble. And in any case, that'll conclude our lecture. So until next time, keep your pencils and your wits sharp.